Let's get started. So today I'd like to welcome everybody for the PhD Defense by Dejan Grubisic. So we'll have about a 50-minute presentation followed by some public questions, and then there'll be a private session with the committee afterwards, I think in a different room. Yeah. Yes. Okay. So there's a meeting right after this. So let's get started.
Absolutely. Thank you so much. First, I would like to welcome everybody for my thesis dissertation, our committee members, professors, friends, and colleagues. Today, I'm going to talk about machine learning applied to compiler optimizations. And I would like to introduce committee members John Malcolm, Chris Germain, and Grace Mark. So without further ado, I would like to start. First, we are going to talk about some introduction why we need machine learning in compilers. Next, we are going to showcase the three contributions of this thesis defense. And finally, we are going to finish with some conclusions and remarks of this work. So why bother? That's a key question. Recently, we saw development of machine learning with other applications. We saw that it's possible to reconstruct proteins, to create images, generate text. And we also, on the other hand, got a huge development in hardware innovations that should support these applications. And it's not a straightforward question, how do we connect these two? And how do we utilize the most hardware with our current applications, and we even enable them further? So first question is, how do compilers work? This is a simplified scheme. It's much more complex in the real world. So the point is that we start here with some C code, and we are giving that to our machine called compiler. And then on the other hand, we got a set of optimizations that we can use for compilers. And then it somehow magically outputs executable code that can be then executed on machine and be in the real world. So compiler engineers, to make this machine running, they need to do two tasks. The first one is to write optimizations that compiler can use. And the second task is to select the right order of these optimizations so that the right product is the fastest, the application that we are running at the end. And in this thesis, we are going to try to answer on this question, is it possible to have machine learning to help us in this second task, which is to select right optimization passes given a compiler, or to just read the thesis here statement. Machine learning is a viable methodology for optimization that could be used to predict performance optimization strategies, as we say, that don't change program semantics, which is really important. Since this is like a big statement, I divided it in three sub-statements, and we are going to prove each of them through this presentation. The first statement is that we are going to use reinforcement learning to optimize execution time of tensor programs by predicting tensor traversal order. Next, we are going to see the use of large language models that get so popular today in optimizing code size by predicting optimization sequence of LLVM. And third, we are going to show even improved performance of large language models and how can we use better sampling technique to even reach the performance of targeted training data set. Okay, without further ado, let's go to the first statement. So first, let's see what is tensor computations. Tensor is a multidimensional array, and we can apply computations the same way we can apply computation to integers and other types. Here we have tensor A and tensor B. Tensor A is three-dimensional, while tensor B is two-dimensional, and each of them have their dimensions here. And to do tensor computation, it means basically to select the reduction dimension, or like what pairs are we going to compute together and assume, and then we output the resultant tensor. In this case, you can see that we choose a pair on X and pair on Y, and we basically put them together, and each pair is going to result in one square in the tensor C. And then we are basically reducing these two tensors to tensor C. Similarly to this, we can select different reduction dimensions, like in this case, and we are reducing this dimension 4 and 4 into the one dimension, and the final dimension is going to be dimension C, one dimensional 3 times 2. And finally, we can choose even multiple dimensions to reduce, similarly resulting on a tensor, which is going to be basically the tensor, darkened tensor without the reduced dimensions. Okay, now that we defined our tensor computations, let's see how can we execute them on computer. We show tensors through nest of multiple loops, and then in the most inner loop, we define tensor computation, or how we're going to define tensors, and we also need to define reduction dimensions there. And finally, after we do this, we can send the temporary results that we accumulate back to memory. In this case, we can evaluate this loop nest, and we can see that performance of this particular nest on our hardware was 1.2 gigaflops. If we reshuffle this loop order, which is allowed in this computation, and do some hardware-specific optimization like loop unroll or like vectorize, we are able to transform this same computation and speed this up significantly. In this case, we are increasing our performance from 1.2 to up to 49.4 gigaflops. And the question is, can we learn how to transform this starting loop nest to the resulting loop nest that fits our hardware the best? And for each hardware, this transformation can be different. All right. To do this, we built the tool set called LoopStack. LoopStack takes your code in Python, and then it has 3 components. LoopTune is tuning the reinforcement learning network that we're going to talk more in few slides. Then LoopTune is using LoopTool to transform this loop nest, and finally we get a loop nest part which is going to execute and transform this in actual executable code on hardware and execute it. These are the set of transformations that we are using. So first, in order to transform program A to program B, we introduce the notation of agent. And agent is pointing to the loops, and agent is applying the transformation listed above on each loop. Agent is able to traverse loop to go up and down, to swap the loops with the next one on down or on the up, and also to split these loops with a factor that we defined here, which are 4, 8, and 16. This way, the agent can basically go and transform this loop iteratively, step by step, until we finally get something that has good performance. And the question is, can we learn to transform these loops, and can we learn, given the loop structure, what is the next action that needs to be applied until we get to the better? And reinforcement learning is a great tool for this problem. So we define our reinforcement learning environment in a tool called compiler-gym. So first, we need to generate a lot of examples. In this case, we are generating about 2,000 examples of different loop nests with different loop sizes. Next, we are going to give, for each example, the loop tool, and we are able to transform this to different structure. This different structure then can be evaluated on the hardware on a loop nest part. And finally, we can provide a reward signal, which is going to be amount of gigaflops you get for the certain configuration. And now, besides this, we also need to define observations and actions that are applied from loop tool. Observations are basically just how we defined loop nest state. And we're going to talk on the next slide how we do that. And we also say what action we applied so our reward signal changed. Once we have these 3 components, next action, observations, and reward, we can put this together in our framework called LoopTune. and apply reinforcement learning to tune it. We are first quantifying this action space and observation space to a vector, because we can train the neural network only with vectors. And then finally, we can train our policy network, which is going to predict what is the next action given our state that we are operating with. So let's see how our state representation looks like. Here we can see this textual representation, how we as humans represent this computation. And to represent this, we use a graph. On this graph, each square is going to represent one loop nest. And we can focus first on black lines are showing what is the tree structure, what is the loop nest. And in this case, you can see here that on line 1, we have iterator I, and that iterator I is also catching on line 6 for k in range. And that means that loop I needs to point also on loop k to basically say that it's chained together. Next, we have data flow. Data flow is described by blue lines here. And it just tells us how our data from, in this case, tensor A and B, are merged together. We are doing operations. We calculate temporary result. We make a reduction on J dimension. And finally, we return this into back to the memory, which is tensor C. And finally, we have the axis pattern marked with red. The axis pattern is basically how much you move into memory when you do one iteration of a given loop. So in this case, every time we move iterator I in the one step, we are actually jumping for 256 into memory, because the tensor is laid such that dimension 256 is going to be continued further. And finally, once we have representations defined, we need to find a way to vectorize this so we can train machine learning to train the model. So for each loop, we are going to have a set of 20 floats describing each loop. The first float is going to be agent, which tells us if the agent cursor is on that loop. Next one is going to be what is the loop size for the given loop. After that, what is the loop tail, which can happen if you split a loop unevenly and then you have this little tail of computation that needs to be marked as well. Next, we have the bit that describes if our loop is computational or like a drag back to memory. Here, we have this second loop starting from a 6th line, which is just like writing back to memory, and we need to describe those. And finally, we have something called strides frequency, which is basically a cumulative view on how much we jump in memory for a given stride. And in this case, we can see that we are jumping for stride 128 and 256 up to 256 times here. And you basically calculate this, look each vector and see how much they move certain iterator and then how much they jump every time and how much they move the iterator as a frequency now. And you just accumulate this across all the vectors. And this is going to be useful to estimate the memory access pattern and the performance therefore. All right, I hope this was clear. So next, once we get applied functions, observations in vector form, and reward signal that we evaluated our network, we are going to use LLVM, which is reinforcement learning library for training the policy network. And the benefit of LLVM is that it implements popular reinforcement learning algorithms such as PPO, which is proximal policy optimization, Impala, A3C, DQM, Apex, and so on. And then it also provides user, which is us, to define their environment and automatically train the neural network for the given problem, given the examples. So during training, we train our model for up to 5,000 steps. And we can see here how average reward for one episode of 10 steps increased over time on average. So for each of these tuning algorithms, we have one curve here, and we can see that the purple curve of Apex DQN is significantly higher than others, and it converges after around 1,000 examples and increase the performance for about 34.2 gigaflops, which basically means we provided input example and we are asking the network which is trained to predict next sequence how much benefit you can get after 10 actions, 10 steps. That's one episode. And in this case, on average, that's 34 gigaflops. Other algorithms doesn't perform as well. And our winning configuration is just simple multi-layer perceptron with 10 layers. And each layer has a width of 1,000 with a discount factor gamma of 0.95 and a learning rate 1 power minus 6. So let's see how do we compare with other approaches. First, we are going to compare ourselves to traditional search algorithms, which are usually just trying a lot of these different combinations and evaluating them and see which one goes better and then try to extend it further. Next, we are going to compare ourselves to machine learning-based auto-tuners such as TVM, AutoTVM, and Metaschedule. And finally, we are going to compare ourselves to hand-written library such as NumPy, which is written from experts and require a lot of engineering time. For each experiment, we allowed 60 seconds for tuning. So first, search algorithms that we are evaluating are going to be greedy search, which is trying a lot of different combinations, taking the different actions, and every time it takes the action that increases performance. Once the action doesn't increase performance anymore, it stops, and we report that performance back. We have similar algorithm here, greedy with a look ahead of 2, which do the same thing, but instead of using the performance of next action, it is using performance of next 2 actions, and it's possible to have one weaker action, which might open opportunity for bigger improvement later, and therefore avoid some local minimas. And we have also beam search, beam DFS, and beam depth research, and beam breadth research, which are just different traversal techniques to navigate the action space. And finally, we have the random search, which is trying a lot of different combination sequences of action, evaluates all of them, and reports the best one. So to see these results, we are showing here the performance in gigaflops on the top graph, and how much time it took for tuning on the bottom, on the left. And you can see that for the plots that are in red, higher is better, and the plots that are blue, lower is better. So for performance for gigaflops, you can see that our loop tune is light green, and it's achieving much higher performance than traditional search algorithms. And on the below part, we can see that time of our approach loop tune is about 1 second, 10 to the 0, which is 1 second, while some other approaches here require much more time and still not performing as good. And the graph on the right is just summarizing this performance. For each of the algorithm, we have a violent plot, and we can see that at average, loop tune is achieving 3.2 speed up compared to the original loop nest, which we use as a backend. So this performance reported here is performance that loop tune is adding strictly on top of our backend, and it's not what our backend already brings when it comes to optimizations. Okay. Next, we are going to see how our framework compares to machine learning auto-tuners and hand-coded libraries. On this graph, we have again how much time it takes for compilation or auto-tuning. And on the right side, we have execution slowdown ratio. I'm going to explain that in a second. When it comes to compile time, on the x-axis, we can see how much time at average it took to compile and tune the examples. And on y-axis, you can see the percentage of test cases from 0 to 100. And they're sorted by their benefit. And here, the left is better. So you're trying to decrease your compilation time for as much examples in test set as you can. And we can see here that LoopTune is red. Again, is able to predict the best configuration in about 1 second, while other auto-tuners such as Method Schedule and AutoTVM requires significantly more, in this case about 30 seconds and 60 seconds at average, while some other requires even less than 1 second. Here we can see that NumPy, which is hand-coded library, achieves the best results, and it takes 10 to the minus 4. On the right side, we are showing similarly the performance. So whatever methodology was the best, is going to be closer to the left side. And if you got, for some example, the best performance, it's going to be showcased here as a slowdown ratio of 1. If you are twice as worse as the best one, your data point is going to be on number 2 here. And then on y-axis, we still have best case examples from 0 to 100% of them. And we can see here that LoopTune here is the most close to the left line, which means it is number 1 for majority of examples. Only for maybe less than 40% of examples, it's beaten by some other auto-tuner, while NumPy as a hand-coded library is slightly worse than this. So this is a significant result because we were able to automatically create methodology that outperforms hand-written library such as NumPy in this case, with reinforcement learning method and policy network, which is going to work next with some new architecture. And we are not going to be in need to hand code everything from scratch every time, but we will be able to just apply methodology and train this automatically. So sum this up. LoopTune generates code in less than a second. It outperforms other techniques, popular auto-tuners such as TVM, Method Schedule, and AutoTVM for 9x, 2.8x, and 1.8x, and matches the performance of NumPy without inducing this cost. When it comes to limitations, we constrain our problem such that loop bounds are known in the compile time. So that means that there is no if cases in the middle of the loop, and everything can be, computation is defined statically. Training time is also proportional to how much time it takes for you to execute the loop. So here, our training is going to be shorter for loops that execute more quickly, while if you have some larger loop, larger computation, you might want to use some cost model for that, which we can talk later about that. And for now, it's only CPU only. In future, we can extend this to GPU or other architecture by using exactly the same methodology, just having different support on our backend tool, and the option space and everything stays the same, and training stays. Just need to retune our model for any different hardware. So we did finish the first part, and we proved that reinforcement learning can optimize execution time of tensor programs by predicting tensor traversal order. Get the zip here, and then we can continue to the next one. Okay, next. We are evaluating the power of large language models in predicting LLVM optimization sequence in optimizing code size. So here we have, again, the picture of our compiler. And the problem now is, given the code C, can we predict the right order of these flags that we are using to feed our compiler? And for each program, this sequence can be different. There is about 120 optimizations that you can put in the sequence. And sequence length can be also the order of like 100, which gives astronomically big number, and it's impossible to evaluate all of the schedules. So you need something smarter than this. The key question here is what would be a good representation to represent our code? Traditionally, we have a feature map here on the left, which is basically trying to say what features, how many loops our program has, or how much arithmetic operation it has, or some other features. And then given the features, we might be able to predict what optimization makes sense to do. Next, we have graph representations that are more natural for hardware design, that are also including the control flow and data flow and these kind of dependencies that are not captured by features. And finally, we have text. And first two of these have a problem because they always hide some of the features. If you decide that you're going to have a certain feature map, you're not going to capture all possible programs and you're going to lose some data. The same way for the graphs. But with text, text is uniquely identifying the program and therefore contains more data about the program. Only problem is that we didn't have tools to utilize text because it's unstructured and to predict our optimization sequence. But recently we got large language models which are proven to work on text in natural language, and we thought it might be a good idea to try it for compiler language as well. So this is our problem. We have prompts similar to prompts in ChatGPT, you might try it, in which we say, tell me what passes to run on the following LLVM IR to reduce instruction count. And then we provide LLVM IR assembly code, which is basically a description of our computation. And then we expect the answer that says run passes, graph to mem, Sora, simplify control graph, and so on, to reduce instruction count from 15 to 4. And then we expect our model to output how the optimist code is going to look like in LLVM IR. After we do this, we first create a lot of examples, about 1 billion of examples, which has both prompt and the answer. And then once we train that, we go to the inference. And in the inference, we can just run our model and generate the first part of the answer, run passes, and then we can stop there because at that point, we already know all the passes that are necessary. And then we can take just compiler and compile them and see what code we get. This way, we are keeping semantics of our code because we assume that passes are going to be idempotent when it comes to semantics for the code. And we are able to just see if these strings of passes are in our dictionary. It's pretty easy to check that. And usually this can immediately create optimist code with compiler. And when it comes to these passes that we are showing here, what do we expect? We use autotuner. That traditional autotuner spends about 13 minutes per example, just trying different optimizations. And then once we find the best optimization, we say this is a training example. And then the benefit of the model is that we don't need to autotune anything from now on that has similar structure. We can use our model and it will produce in few seconds result that autotuner built data for before. A bit about the model. So our model has architecture of Llama 2 model. It has 7 billion parameters. And training set, as I said, is about 1 million of examples. So I said billion before, now it's a million. And then training set is a textual form of IR representation. And we are expecting to produce passes, instruction count of starting code and instruction count of optimist code, as well as optimized IR. We run our training from scratch for 30,000 steps. And through our model, we have 15.7 billion tokens that goes through. Each token you can think of about one word, let's say in natural language. And this takes us 120 GPU days to run. Of course, we don't run this on one GPU for 62 days. We run this in parallel or multiple GPUs. And this was done, I think, in a day or two when it comes to training. So let's see how our training curves look like. So as I said, we have like this 114 billion tokens that goes on x-axis during the training. And you can see the performance, which is improvement over -OZ, which is default optimization that our compiler uses. The auto-tuner performance that we use for training set is about 5.9 or 6% over -OZ, while the performance of our model increases with time and reaches 4.4 less instruction than -OZ optimization, which is default for compiler. We are comparing that. As I said, we have 5.9 for auto-tuner, but it requires 27 million compilations on 1,000 validation sets that we evaluated during the training. We also wanted to see our performance when it comes to predicting instruction counts and the code we are trying to generate here. And when it comes to instruction count, we are able here to show that predicting the error in predicting unoptimized the input code goes to zero pretty quickly, which means that our model is able to learn quickly how many instructions has starting code, and then the error for optimized code reduces to 5.9% during the training. When it comes to performance of code metrics that we generate, we are here following the blue score, which is basically a similarity coefficient between code that we expect and code that we generated. And that metric goes pretty quickly to 95%. That means they're pretty similar. We have the green line, which says how many of the examples of these 1,000 validation functions compiles without errors, which is 90%, 90.5. And then finally, we have exact match, which is 70%, which means how many of produced code by model is exactly equivalent to the code that would be compiled with compiler, given the optimization passes that we predicted. And this number is 70%, which is very high. That basically means that the model was able to reproduce result of compiler exactly for 7 out of 10 examples, which is pretty high. And we don't expect that to see from the model. Okay, so let's see now evaluation on a full test data set we didn't use for training that has 100,000 examples. So here we're going to show performance of this auto-tuner that we used for training, and also two state-of-the-art auto-tuners such as AutoPhase that use reinforcement learning that we mentioned in the first part. It uses vector representation with 56 features to describe code. And also we have a core set MVP, which is use iterative search and trains post function to evaluate how good is the given configuration using a convolutional graph neural network. And finally, as I said, we evaluate this in 100,000 test examples from various data sets that we can talk later. So these are the performance. On the left side, you can see how much compilations it takes for each of the methods. The auto-tuner requires about 2.5 billion compilations for all 100,000 functions in dataset. AutoPhase has 4.5 million. Core set MVP has about 400,000. And our approach is zero because we don't use compilations. We are predicting directly the text. And when it comes to performance, auto-tuner on this 100,000 data set has performance of 5.03% improvement over -OZ. AutoPhase and core set actually regress the performance, which means they're worse than default optimization. And in our approach, we were able to get 3.03% improvement with having just 0 compilations. We were curious what happens if we don't have regressions. So we just simply added this minus OZ backup, which just means if any of the models produce something worse than minus OZ, you take minus OZ instead and report this performance. And then each of the methods are going to have positive input now over OZ, and we can still see that our approach is the best right after the autotuner compared to autopace and corset. We have had some additional experiments that are trying to answer these following questions. First question here is the flag frequency that we are generating by the model actually similar to the frequency of flags that are in our training dataset or produced by autotuner? After that, we are going to answer how model optimize larger programs compared to the smaller programs, because it's more details there to think about. And after that, we are going to say how much training data contribute to performance. Do we need more data to train the model or less data? And finally, does generating this second part, the optimist code in our answer, helps or not? So here we can see the frequency distribution of different optimizations for autotuner and for our approach. And you can see that actually frequencies of different flags are really close to both autotuner and our approach, which means that our model is able to know roughly how frequent some flag is and to apply them in certain context. So the answer is yes. Next, we are asking, can model optimize larger programs equally good like the smaller ones or not? And you can see here on x-axis unoptimized instruction count and how unoptimized instruction count grows towards the right. We can see that our performance, which are in pink here, also grow, which means that larger programs are actually more optimized than smaller programs. And the reason for this is simple, because if you have a larger program, you can shrink it more. But also your model needs to get more data. So the answer is larger code means higher improvement. Next, we are asking how much training data contributes to performance. And we trained different models with less data. And you can see that with less data, we are getting less performance, which means in future, maybe if you would collect even more data, you would be able to achieve even better performance for this, seeing the trends here. So the answer is more data, also higher improvement. Next, we are evaluating the performance of the model, which is trained with an answer that includes the optimist code and that just predicts the flags and instruction counts. And you can see that performance actually deteriorates if you don't produce generated optimist code. And we believe that the reason for this is that if you are forcing model to produce correct code, which is optimized, you're forcing the model to learn more about the structure of the code and therefore produce better results. The answer is the generating code helps. I have 4 more questions, and this is going to be enough for this section. The first question is related to the quality of generated code. Second one is going to be what kind of the errors are most common by the models. And we are going to show 2 examples of common errors and 1 success generation that is kind of complicated. So for first question, here we are showing how the code generated having different performance. So on x-axis, we can see the performance of generated code. So you have on the left side code which performance is equal to minus OZ. In the middle are the programs that are which performance is better than minus OZ. And on the right are the programs which performance is worse than OZ. And on y-axis, we are showing these 3 metrics that are evaluating the quality of generated code. And we can see that these metrics, the blue score and how many code compiles, are decreasing when our produced passes are worse than -0.7. And the optimized instruction count that we are trying to predict of optimized code are increasing. Their error is decreasing, which basically means that if you generated code which is worse by blue score, you get lower performance, which are worse than -0.z here for the given program. That basically means that if model doesn't know to generate appropriately, like the optimist version of the code, most likely it will have problems to find a good optimization sequence for that code as well. When it comes to errors that are common, the most common are type errors. Type errors usually include just like int before some variable or something like that. And we have the most error there. Next, we have instruction forwarded references, which means something is referenced before it's defined in output code, which means that the language model cannot really know what is the order of these sequences, and so on. We have undefined value. But the answer here is that type errors are the most. Finally, we can see an example of one other common error, which is evaluating mathematical expression. You can see here that we are storing this large number in a register, and then we use this trunc operation, which is truncating this big number. And we expect the green one, which is 165, to be the answer, while our model predicts 1. And the reason for this is that large language models are inherently weak in mathematics. They didn't get enough training data, and they're not trained to do mathematics at all. In future, this might be helped by using tools and training language models to use tools like calculator or like some kind of program interpreter. But we can talk about that for future section. This is one and last example of successful generation. So we are starting here from extremely complex code. The structure of code looks like this. I guess this is easier to understand. We are starting from variable 0. We have some function to function tail. And then we have some branching there in these blocks 9 and 11, then block 12. And when we are applying -z optimization, we are getting code on the right side, which is significantly shorter. And then you can see that it has changed this part, which is explicit branching here with jumps, to compare instruction and select instruction. And our model was able to learn that and correctly predict this code. To conclude, large language models can predict performance optimizations. We can see here that we get about 3% of improvement over Z with 0 compilations, while the autotuner gets about 5% with about 2.5 billion compilations. Next, language model has strong coding and reasoning capabilities that we did not expect before. It has 91% of compilable code and 70% of codes that are exactly the same as compiler would optimize. And when it comes to challenges, we were operating on a functions that has less than 2,000 tokens, and we're able to capture the functions of, let's say, up to 50 or 60 lines of the code. They are growing like research community, which is trying to increase this context size that we can handle with retrieval augmented generation methodologies and so on, which are promising that is going to expand in this direction. And the next problem is that large language models have problems with math. This is also maybe solved today because some language models were able to use like tools such as calculator. Some results have shown that it is possible to combine two together. With this, I would finish the second part and conclude that a large language model can efficiently optimize the code size by predicting the sequence of LLVM optimizations. All right, and we have one last part, which is how can we use large language models to even more improve the performance and even more optimize the code size by using some smarter sampling techniques. First, we are thinking like, what can we do when it comes to our generation with our large language models? And the first idea is that we can just analyze the code and metrics that are generated from the model, and then we can see if they match together. We can see here if the sequence of passes generated are valid or not. We can see if the predicted instruction count of beginning code and the code that should be optimized by using this optimization sequence is correct or not. Then we can also see if there is some error if you try to compile the output code. Given all these metrics, we are able to construct a feedback. We have exactly the same task as before. The only difference is that once we generate our code, we have one more pass with the analyzer, and then we construct the feedback that includes all these metrics that we just mentioned, and basically gives the feedback back to the large language model as extra text and gives model a chance to try again. The model is going to now have the same prompt, the generation which is generated there, and the feedback, and try to generate something better. We were evaluating here three kinds of feedbacks: a short feedback, long feedback, and fast feedback. Short feedback is basically the shortest kind of feedback. It just includes the metric in a scalar form. We don't include the code, the generated code, and therefore it's a kind of short version. Long feedback includes this compiled IR green part, which is going to extend the length of it. And the fast feedback is a feedback that doesn't require generation of code by the model. So basically, we can stop after we generate the passes in the first two sentences, and we don't wait for model to generate optimized code, and therefore we are saving time. We are still producing the metrics about instruction count here. When it comes to our results, we can see here that compared to original model, fast feedback has the highest performance, and it improves the original model slightly from 2.87% over minus OZ to 3.4. We use just the performance of the model, and then if you back it up with minus OZ, you increase it even more. But this performance, as you can see, is like not significant. We evaluate this on 50,000 test examples. We are showing on this graph also like how we are optimizing different kinds of data. On A part, we can see that this part of data are data in which autotuner found something which is non-minus OZ optimization pass. In the middle are the data where the original model produced passes that reverse the autotuner, and the C are original model that predicts something that had a wrong target instruction count, the instruction count of optimized code. We can see here that this technique with feedback works the best when original model had something worse than autotuner, and then we provide a feedback, and we can get performance increase from minus 0.2% over OZ to 1.2% over OZ, and so on. So other than this, we were considering also different techniques for generation of the tokens called temperature sampling. Temperature sampling works this way. We're generating each token after the next token out regressively. And for each token that we are trying to generate, we have distribution of how probable is a given token for the dictionary that it is defined. And we usually take the best one in a greedy decoding, and we say, okay, this is going to be the next word predicted by LLMs, and then we continue this. But instead of taking just the best token which is most probable, we can sample also this distribution. And therefore, we can use softmax function, which is normalizing this distribution to be up to 1. And then it samples it and gets one token from that distribution. We can even relax this the temperature factor. And temperature factor is basically just a constant which is dividing these probabilities, and therefore making this distribution sharper if the temperature is less than 1, and making this distribution more flat when the temperature is higher. This basically means that when temperature is high, we are less certain. Everything looks very similar when it comes to probabilities, and our model can produce more different results. Let's say when distribution is sharp, we are forcing our model to predict only few tokens that have like high probabilities. So with sampling, we got these results. So on x-axis, we have the temperature that we are increasing for 0, which means that we are taking the argmax of distribution to 0.6, sorry, 1.6. And on y-axis, we have how much improvement we got. And each color here represents how many samples we are generating for each example. If you have only one sample, which is a blue here, and you're increasing the temperature, your performance is actually going to decrease because you're going to pick a token which is less likely, and therefore it has less chance to produce something good. But if you have multiple tokens, like 2, 3, or 10, and for each of tokens you pick something less likely, it might happen that some of these less likely tokens are actually better in practice. And then they amortize each other and performance grow up. And then for each of them, they have some kind of hill shape in which you saturate at some point, and then increasing temperature starts dropping below, because at that point you are generating tokens at random. And the last part is a better sampling algorithm, which we call priority sampling. There is a problem with temperature sampling, and the most common problems are that temperature sampling creates a lot of duplicates. Given 100 samples, you can create up here in this example 23 minus OZ optimizations, which are wasting samples. Or if the temperature is too high, you can create optimization passes that are not coherent, and you cannot compile them, and therefore also creating illegal sequences and wasting samples. And we're trying here to prevent these two metrics. Here is one more graph that shows how many unique samples are generated if you're trying up to 100 samples on x-axis. We can see here that the temperature sample creates up to 5 diverse samples here, which is really low, and we want all of them to be unique. So for priority sampling algorithms, it works like this. So here, each node in the graph is going to represent a token. Each string underneath is going to be what is prefix to given token, and all the squares above are going to be what are potential next tokens from that token. And then here, every time we are expanding next token, we are sorting the probabilities of next token, and we are putting them on priority queue. We are expanding the best token to the next one, and put to priority queue only tokens that are not expanded. As they are moving on, at some point we are going to finalize the sequence, and at this point we are going to generate, in this case, this sample which says run passes minus loop simplified, which are all the first line up to the black. See, and we put on priority queue all the tokens that are not expanded, and in a sorted way. Priority queue enables us to take the next best, the next most probable token that should be expanded, and then we can expand from there. And then in the next sample, we can just find from where we should expand, and we can continue until we stop, and then create a new sample that way, guaranteeing that each new sample is going to be unique. So we are just taking, every time we create a new sample, we expand from the queue, And we create finally the third sample, which is going to be different from all of the previous samples. One extra little detail that we do here is that we constrain the possible samples using regular expressions, which are not allowing next sample to be wrong. And this doesn't take any more time complexity, but enables us to reduce the possibilities of the next tokens. So these are the final results. You can see here how we increase the number of samples that we are using, for example. And you can see the improvement over minus OZ. First, we get the random sampling, which tries up to 100 different optimization passes. We have the model, which is yellow straight line, which is the performance that we had of original model. And then we have the performance when you use a temperature from the green line up to another green line, which is basically how much performance you can get using different temperature techniques. And with priority sampling, you have this red line, which dominates the performance. Even around 30 samples, it outperforms the performance of autotuner that we used for training. And this was not expected because we were trying to replicate the performance of autotuner, not to outperform it, but with enough samples and enough randomness, you're able to get even better performance. So with this, the final takeaways here would be that we tried three feedback formats with a slight improvement over original model, not significant. When it comes to temperature sampling, we were able to get up to 98% of autotuners improvement. But the problem of this is that we duplicate. We have duplicates. We also have illegal generations. And also for each problem, you need to find what is the optimal temperature, which requires extra computational effort. While in our case, it's deterministic and always produce the same results. Priority sampling has no duplicates for illegal sequences. With 5 samples, you're 95% improvement of autotuner, and with 30 samples, you're outperforming your autotuner here, which tells us that we are able with smarter sampling techniques to significantly improve performance of a large language model here for training. And with this, I will just conclude here. During my PhD, I've been able to work on these 3 topics. First, we were showing that with reinforcement learning, we are able to generate code in less than seconds and outperform state-of-the-art autotuners such as metaschedule TVM. With limitation that we just implement at this point CPU version. Next, we show that large language models are a viable optimization analyst and like a helper here. And we are able to get up to 3% of autotuner. We are able to show that the large language model has strong code reasoning abilities, creating high 91% of compiled code and 70% of code which has exact match to compiler. With limitation that we have short context size and we don't have support for evaluating math expressions inside large language model. And finally, with priority sampling, we were able to get up to 5% improvement over OZ with 30 samples. We don't generate any duplicates or illegal samples. And only limitation that we have at this point, that current implementation is sequential, which can be further parallelized, and we can work on that in future.
Okay. I want to catch you up here because we need to have a little time for questions before someone grabs the room. I don't see them outside, so we've got a few minutes.
I think we should take an hour and a half for this.
Oh, I'm sorry. We're set in this room. I thought that we were.
Yeah, I thought you said an hour.
No. I think that's an hour and a half.
Oh, okay.
For this room, and then we have another room for half an hour.
Okay.
Yeah, I'm sorry. I took some time here. Okay, but before I finish, I need to say one big thanks to everybody who helped me on my way. First, we have our great group with John as a team lead. It was a great time, and I would personally like to thank John for helping me debug a lot of hard problems in APC Toolkit. And I had pleasure to collaborate with all of these people on some parts of my development and my PhD. And next, I would like to say thanks for all of my advisors. I did 3 internships with my PhD. First in Berkeley Lab with Brian Austin. Next, I had internships in Facebook in New York with my advisor Alexander Zlatevsky and Brian Lusty. And last summer, I've been in California with Meta with Chris Cummins, Volker Seeker, and Hugh Letter. And without them, I wouldn't stand here, and definitely I wouldn't have all these results. Next, PhD and internships wouldn't be as fun without people. I had great pleasure to meet a lot of people working with me together in Meta offices in New York and Menlo Park. Thanks to all of you for coming here, for being the part of my PhD program for 5 years. It was interesting. We had enough time to start some new tradition like roasting lamb on Easter in Valhalla. I would also like to thank the Serbian community in Houston for supporting us, organizing a lot of events. And they're the reason as well for me being here. I would personally like to thank Vesna Kamirkovic and Zoran Budimnic for bringing me twice, and everybody else for great time. And last but not least, thanks all my family for constant support from abroad and from my brother who's here and being next to me all this time since COVID happened. And with that, there is one more thing. I need to thank these little creatures that helped me a lot. I'm proud father and stepdad, if that's the right word, of 3 cats. You can see Sieva, Mocha, and Sasha. They were super, super supportive when problems get wrong. So you can see me like trying to code, and Sasha was always, keeping me there. So at this point, I would like to stop and open the question time. Thank you so much for your.
So I'll ask. So in doing machine learning, normally you think of this as you have a large data set of examples, and then you've shown a new pattern, and through some magic that nobody understands, you come up with some kind of answer or something. So where do you store the answer? Is this like, do you have is it stored in the cloud, or do you pre-compute some number of examples and store them in the compiler, or what?
Yeah,
what I'm asking is if I want to, so I take all this, I put it into my compiler, and I give you a piece of code, and I say compile it. Does it go off to the cloud? Does it find a bunch of stuff, or is it?
Great question. So the question was, how do we store examples when we're training the models? Are they stored on cloud? Are they stored locally on machines? So in all these examples that I'm showing here, we were storing locally examples on a disk. Because it's a text form, it doesn't require a lot of data, maybe up to a few gigabytes, not more. But when you're doing training, you want to send and broadcast these examples from usually JSON-L file or some other kind of file that you're storing the prompt and answer, or like some kind of representation plus code to different GPUs and different nodes, and then you're training this in distributed fashion. But before that, examples are stored locally into your files.
Okay, but the size of the data set would restrict on where you could run it or something.
So I think the question that you're looking for is how do you store the results?
Yeah,
the results.
Not well. Well, depending on how you do this, you could pre-compute some number of results and just store them locally in your compiler, or you could have a much larger data set that you go off to the network in the cloud and do something. So
here in our problems, we didn't use data sets that have, for example, images or some other data structure that requires much more memory, like video and stuff like that. So text is pretty friendly when it comes to memory. The one thing that we also need to think here is the weights of the model. 7 billions of the weights is also quite a number. And usually you cannot store large models even on one GPU when you're running the model. but each of those are just stored in a normal like CPU memory. And then when you have a training, you just upload it where it needs to go. So yeah, that would be the answer. Does it make sense?
Mm-hmm. So the result is a vector of weights for each of the levels of the neural network. So
yeah. Yeah, I think that PyTorch has some format like PTX or something that they store. And then basically it knows what weight corresponds to what like layer and stuff like that. And then it's able to upload it on GPU when we're running inference. But all of these are just like a files normally stored on CPU.
Question for the reinforcement learning piece. So it looked like the PR being tested on one of the really state-of-the-art good models, and the majority of them really underperformed. I forget exactly what the purpose was.
Yeah.
You have some questions for why this specific model is some of the two things.
Yeah. So the question was, I don't know if I should go back to that slide. So the question was, why does in reinforcement learning Apex DQN outperforms all the alternatives, and why the curve goes like up to I think 34.2 gigaflops, and everybody else goes like more flat. The Apex DQN works with something they call replay buffer, and each time you're doing like reinforcement learning, you're trying different sequences, and they're memorizing what sequence was most surprising, and then occasionally it rerun that sequence, like retrain the model on the given set of sequence, and therefore the model more quickly learns. So basically, you're trying to remember the key feature where the entropy between expected reward and given reward was different, and then you just like occasionally retrain on those. So that would be the answer. Okay. Yes.
With that in mind, I don't expect you to run this experiment to be really expensive, but do you think something like a 3-den, if you gave us more time, would also promote that same about 34 gigaflops?
Yeah, that's a great question. The question was if we would give it more time to after advantageous critic. Yeah, it would work better. At this point, it's hard to say for me because I didn't try it. And it requires a lot of like time and effort to run those models. So the most honest answer is I don't know. So I guess there is only one way to figure it out. So thank you. Any more questions?
I have questions, but it's not me for a long time. So one question is, you mentioned that you're using text-based representations of LLVM-IR. LLVM-IR is a graph. So, like, it seems weird to me that you started with a graph and now you turn it to text so you can feed it in subjective and see. So can you, like, explain the insight behind why we need to move away from, like, yes, it works, but, like, shouldn't everything work better if we start with the original graph framework?
Yes. So the question was, if you are trying to use LLVM-IR representation, LLVM-IR conceptually operates on graphs, and that's more intuitive structure for compiler optimization. So why it makes sense to use text-based representation in which we are kind of losing this graph structure? And I think the answer there is because with the graph model for machine learning, such as programmable, the only way we can learn is basically to combine nodes, do some kind of convolutions, and then to predict if this graph is good or bad, or like if the link is missing in a graph. And we can try to predict node representations, but it's hard to predict what action would go well with this. And especially like it has other problems. For example, I think in graph convolutional networks, if you're expanding your features too far, everything becomes looking similar. So there are some problems there, but with large language models, we didn't know in the beginning that this is going to work out at all. So idea was just that let's try it out and see like how it works. The text that we have here is kind of similar to each other. Also, when you see some like optimization compared to the original code, optimization tend to be smaller always. You always can shrink. You always eliminate some instructions. You usually keep some variables in order. And we've been able to show that this is the case also with language models. I don't have exact answer, like maybe some combination would be better, like some performer or something like that, but we still don't know that. And also I need to say here that we're also clearing up a little bit data on text side. So we are removing the comments, white spaces. We are moving some constants, for example, that are too long with some kind of macro that is predefined, and then we return back after. So there are definitely questions, how do you prepare data for this task? But here we are showing that it's possible to use also language models. Is it the best option? I don't know, probably not, but it's definitely the beginning of research area. So hopefully in future we'll get better answers.
Maybe one last question from Luigi.
Yes.
Yeah, I just want to kind of clarify that. So you mentioned this outperform the other tools on the first computer, and then there are some seconds. So when you talk about outperform or improvement, I'm talking about like the generating the code runtime performance, or you mean more on like generating fewer lines of code, or maybe the first one is the tool itself takes less time to generate?
Oh, yes, a great question. So the question is, if I understood it correctly, if the improved performance means faster tool, or improved performance means like improved by what metrics? The answer here is that with reinforcement learning here, we are better than other tools for both compilation. So we are faster in searching for the right optimization path. And then with that path, we are matching the NumPy library. So the win there is that we are more fast in producing the answer, the output tuning. With language model, that's also the case. So we are shortening the search time from 13 minutes, for example, to 5 seconds, which is the inference time of the model. So the answer is basically with our tools, we are able just to reduce how much time it takes for us to find the good optimization strategy.
But also the performance metric that he was using was code size. So,
oh, yes,
so
yeah.
you were correct. There was an instruction count rather than code performance.
Yes. For language model, we focused on code size because that was much easier to collect. And in order to collect the runtime for LLVM IR, we would need to build this code and to run it, and it would take significantly more time to get a number. And code size is the first step, but in future, we should work on as well, extending this to code size and the parallel execution. So.
Okay, I think we're going to have to break there. Let's thank Dejan again. We'll switch to the private session. Well, let's get started.